Generalized Least Squares, Multiple Linear Regression and Structural Analysis.
This is the fourth geostatistics course about kriging and cokriging interpolation and mapping. Remember that you have available the first lesson that it was about ordinary kriging, the second lesson that it was about universal kriging, and now we are working on the third lesson that is about regression kriging. In relation with the third lesson, you can watch the introduction, also how to create a grid using a shapefile with R and QGIS, also the ordinary least squares, and now today we are going to be working with the generalized least squares. The goal of this lesson is to provide you the tools and also the knowledge to apply for the generalized least square models. Also, we are going to see how the generalized least square model is a better option when we are dealing with spatial autocorrelation. At the end, we are going to make a comparison to see what is the improvement of using the generalized least squares in comparison with the ordinary least squares. All the analysis is going to be executed with RStudio. But at the end, we are going to export the final raster file associated with the trend surface of the generalized least squares to QGIS. Because at the end, what we want is to integrate the information that we are creating with R in QGIS. If you want to have a full understanding of this lesson, I highly recommend first to watch the previous lesson, that it was about ordinary least squares, because this lesson, this one, is a continuation of this lesson. Then it doesn't make any sense to watch this tutorial if you didn't watch previously this tutorial. Remember that if you want to have full access to the courses, just go to the GLS-RK community website at gscourse.online, go to courses, get enrolled at the fourth geostatistics course, interpolation and mapping of kriging, cokriging. Then when you get enrolled, you are going to be ready to start learning. And here we have already all the lessons that we created for this course. Then the lesson 0 is the introduction. Then you have the lesson 1 that is about ordinary kriging with 2 hours 30 minutes of content. Then you have the lesson 2 that is about universal kriging with 4 hours 30 minutes of content. Then you can go to the lesson 3, and in lesson 3 we have different parts. At the part 0 you have the introduction to the regression kriging. Then at the part 1 you have how to do the interpolated grid using R and QGIS. And the second part, you have the ordinary least squares. And today what you are going to see is the part 3 that is related with generalized least squares. Currently, for the lesson number 3, you have already more than 4 hours of content. Also, remember that at the bottom of the lessons, you have this tab over here, exercise files, where you can download the scripts that we are using at this lesson. And that is going to happen for each of the lessons, right? You have all the information that we are using for all the lessons and can be downloaded in this tab. However, if you are not interested in getting enrolled, you can even follow the lessons through the YouTube channel at the GLS-RK community. Then go to the tab videos, and here we have all the lessons. But the only inconvenience is that the videos you can see on YouTube, they have some restrictions. They don't have all the content that we offer at the GLS-RK community website. But you can still follow the courses watching these videos. The regression kriging assumes this model, where the variable of interest located at the space is equal to a deterministic model plus an stochastic model. The stochastic model is the probabilistic part of the model and can be solved using ordinary kriging. And the deterministic part of the model is the trend surface, and the trend surface can be estimated using different types of deterministic models. At the previous lesson, we was working with the ordinary least squares, and we saw that if we want to use this type of deterministic model, we have to cover some assumptions. These assumptions were the linearity of the data, the normality of the residual values, the geostatistics of the residuals, and also the independence of the residuals. It means that the residuals cannot show any spatial correlation. However, in our example, based on the Wolfkamp aquifer dataset, we didn't cover the assumption of constant variance. As we saw at the previous lesson, the residuals from the ordinary least squares has geostatistics. Then in this case, we cannot use the ordinary least squares to predict the trend surface. In addition, we didn't cover also the fourth assumption based on the independence of the residuals, because as we are going to see in this lesson, we have spatial autocorrelation. Despite of having the graph related with the residuals against the fitted values, not showing any pattern, and also having the bubble map related with the residuals that are not showing any spatial autocorrelation, we are going to see that with the semi-variogram, the spatial correlation of the residuals based on ordinary least squares is evident. Then the next point is, if we cannot use the ordinary least squares to estimate the trend surface, what other deterministic models we can use? For example, we can use the weighted least squares when we are covering the assumption of linearity, the assumption of normality, and also the assumption of having no spatial autocorrelation. Then in this case, we can deal with data that is showing geostatistics, okay? But in this course, we are not going to work with this deterministic model. We are going to work in this lesson with the generalized least squares. With the generalized least square, we have to cover the assumption of the linearity and also the assumption of normality of the data. But we can use this deterministic model when the variance is not constant and also when we have a spatial autocorrelation on the residuals. To introduce the generalized least squares in this fourth lesson, I would like to read this very general definition that I got from Wikipedia about the generalized least squares. In statistics, generalized least squares is a technique for estimating the unknown parameters in a linear regression model when there is a certain degree of correlation between the residuals in a regression model. In this case, ordinary least squares and weighted least squares can be statistically inefficient or even give misleading inference. At this point, I would like to make some comments. If we have a spatial autocorrelation on the residuals, we cannot use ordinary least squares and we cannot use weighted least squares. Then, if we don't have a spatial autocorrelation, we cannot do regression kriging because we cannot use the stochastic part of this model. Then we are going to work exclusively with the deterministic part of the model. Then we can use any type of deterministic model. Could be, for example, the triangulated irregular network, nearest neighbor. Could be, for example, any polynomial surface, also the weighting inverse distance, splanes. There are a lot of different deterministic models that we can use, but it's not going to be regression kriging because when we don't have a spatial autocorrelation, we cannot use an stochastic model. Then when we are dealing with data that is showing trend and the residuals has spatial autocorrelation, we are going to use the regression kriging, but for the deterministic model, we are going to use the generalized least squares. Then when dealing with regression kriging, most of the time we are going to use this model because we cannot use ordinary least squares and we cannot use weighted least squares. Then most of the time we are going to work with generalized least squares. Another important thing is that in this course we are not going to explain the math behind to the generalized least squares because it's quite complex and it is not part of the scope of this course. If you want to get deeper on the generalized least squares, I invite you to make your own search on Google because there are a lot of information. You have to understand that when we are moving from more general models like ordinary least squares to more restrictive models like generalized least squares, the complexity of the math are increasing, okay? As more restrictive is the model, more complex is the math behind the model. What we saw at the previous lesson is that the ordinary least squares has a very simple and understandable math behind the model. And for the generalized least square, what we can see in general is that this deterministic model allow us to introduce the structure of the residuals inside the model. Then at the end, this model is going to provide better coefficients according to the spatial autocorrelation of the residuals. It doesn't mean that this model is going to remove the spatial autocorrelation. That is not going to happen because if we don't have a spatial autocorrelation, we cannot do regression kriging. But what this model is going to do is provide the coefficients according to the spatial autocorrelation that we have. Now let's go to see an example with the Wall-Kampf aquifer dataset. Before to start with the coding, I would like to show you first what things we are going to see today. And I created this flow diagram to show you all the information because the generalized least squares is a little bit confusing. Then the first thing that we are going to do is to create the model associated with the second order trend surface for the ordinary least squares. We are going to do with the second order trend surface because we decided at the previous lesson that this model it was the best. Then with this model what we are going to get is the coefficients for the model and also the residuals. Then with these residuals we are going to create the omnidirectional experimental semi-variogram associated with the second order trend surface of the ordinary least squares. Then we are going to analyze the structure of this semi-variogram and we are going to fit on the data two different models, the exponential model and also the spherical model. Then we are going to get the structure for this model as you can see over here. Then we have a range that is 42,000, but you have to be aware that the real range for the exponential model is this value multiplied by 3. And then we are going to get the effective range. And that one is going to be the real range for this model. And that range is going to be around 120,000 over here. Then also we have specified here what is the nugget for this model, that is almost 900, and also what is the partial seal, in this case is 2,500 approximately. Then if we make the summation of the nugget plus the partial seal, what we are going to get is the seal, okay? And here we have specified what is the model, in this case is the exponential one. Remember that when we are using the exponential model, we are going to reach the 100% of the seal, because the semi-variance, the model is going to be asymptotic with the seal. Here we have the structure for the spherical model. After fitting the model, we have this information over here. We have the range that is close to 100,000 over here. We have the nugget effect that is a little bit higher than the exponential model, and we have the partial seal that is a little bit small than the exponential model. Then again, when we plus these two values, we are going to have the seal. In this case, we are going to reach the 100% of the seal. Then when we have the structure associated with the second order trend surface from the ordinary least squares from the exponential model, we can take this information plus this information over here. We can put these two things together and we can create a generalized least square model. Okay, in this case, this model is associated with the structure of the exponential model. Then here we have the generalized least squares fit by the restricted maximum likelihood. Okay, then here we have also the exponential spatial autocorrelation, that is this information over here. Then when we plus this information from the second order trend surface of the ordinary least squares plus the autocorrelation of this model, is this information over here, we are going to get a model that is the model of the generalized least squares that is going to provide the coefficients of the model over here plus the range and the portion of the nugget. This portion of the nugget is how much the nugget represent in comparison with the total seal. And what we can see in this model is that the range for the generalized least squares is this amount over here. And the portion of the nugget is this amount over here. Okay, and as you can see, these values doesn't make any sense. That is indicating that the exponential model doesn't work in this case for the generalized least squares. It is very important to compare the range that we get in the generalized least square model with the range that we get on the ordinary least square model. And as you can see, this range is totally different to this range. As these differences are very significant, we can conclude that we cannot use the exponential model to create the generalized least squares model. Even you can see here that the nugget represents around 30% of the total seal, right? But in this model, this number doesn't make any sense. Now let's go to see what's going on with the spherical model. We are going to do the same. We are going to take the second order trend surface model plus the structure of the spherical model, and then we are going to get the coefficients for the general least square model, and also we are going to get the range and the nugget. In this case, this range, as you can see over here, this number is the same as this one. This range is pretty similar to the range that we get over here. And also the portion of the nugget is this value over here, is the same as this one, is also pretty similar at the value that we get over here, right? Here the portion is going to be around 30% of the seal, right? And as these two values are pretty similar, we can say that the spherical model, the structure of the spherical model, works in the generalized least square model. Then as that one is working, we can move to the next step. We have to understand that the generalized least squares is a little bit complex model, and sometimes it provides values that are not realistic. Then the goal is to verify that the information that we get, the structure that we get, is the adequate one. Then that's the reason because we decided to compare this structure from the generalized least squares with the structure that we get at the ordinary least squares. And we want to see that they are quite similar, right? And also, another step that we want to take is to take the residuals from the generalized least square model, create the omnidirectional experimental semi-variogram, and then fit the model in this experimental semi-variogram in order to see if the model that we fit over here has the same values for the structure as the values that we get over here in this model, right? We need to compare that one because these values over here from this model has to be pretty similar at the values that we are going to get at the spherical model when we fit the spherical model on the residuals from the generalized least squares, right? Then what we are going to do is to take the residuals from this model, create the omnidirectional experimental semi-variogram. Then with this semi-variogram, what we are going to do is to fit the spherical model. Then after fitting the spherical model, we are going to get the structure. Now we want to compare these values with the model of the generalized least squares. Then here for a range, we have 150,000, and this value is pretty similar to this range over here, that is 124,000. And also we want to compare the portion of the nugget. The portion of the nugget here is 1064, and it represents, as you can see over here, the 25% of the seal. Then if we compare this 25 with the value that we get over here, that is 23%, we can say that they are pretty similar values. Then we can conclude that the structure of the spherical model from the ordinary least squares is working properly for the model of the generalized least squares, because the values that we have in this model are pretty similar as the values that we have in this model. Also, if we want, we can adjust the spherical model on the data to have values over here that are closer to the values that we get at the other model. But in this case, I decided to fit the spherical model automatically. But you can fit manually, and then you are going to have values that could be a little bit different over here to have a better approximation to the values that we get at the other model. But as the values in general are pretty similar, I was thinking that it was not necessary. Also, I did an experiment, and I took the residual values and I fit also the exponential model to see what's going on. And what you can see over here, that it provides an unrealistic range. Remember that we have to multiply this range by 3, and this value is going to be higher than 300,000. And that value is not realistic for the range, right? And also, to conclude this section, I would like to compare the spherical model of the ordinary least squares with the spherical model of the generalized least squares. Then if we are using the ordinary least squares, what is going to happen is that we are going to underestimate the semi-variance, because as you can see, what we have over here is that the seal is around 3,200, but with the generalized least squares, the seal is about 4,200. Then here the semi-variance is 1,000 bigger than here. Then if we are using this model to do the ordinary Kriging, we are going to underestimate the semi-variance. We are going to lose all the structure over here, all this structure that we have here, we are going to lose if we are using the ordinary least squares, because the semi-variance in this model is 1,000 less than in this model. Now it's time to see all the coding and scripts I use to create all this analysis. First step is open RStudio. And now I am going to create a new project. New project, new directory, new project. It's going to be generalized least squares, and I'm going to save in a different folder. It's going to be this folder. Here I'm going to create a new folder that is going to be generalized least squares, and I'm going to select this folder and create the project. And now I'm going to open the windows for the scripts. Now I'm going to paste all the coding I did already, and we can start to run the scripts. Then we are going to start over here, generalized least squares. We are going to load the data. Here, load the data set. The data set is located in this link over here. This link, and the name of the file is this one. Okay, and also I'm going to show you the folder. This one is R4, is this folder over here. 4, 3 data set. Inside this folder I have this spreadsheet that is the data set. Then I'm going to create a backup that is going to be called as a A2. I put A because it's pretty easy to manage the name of this spreadsheet, right? Then I created the backup, and the next step is to plot the data in a graph. Then I did this graph with ggplot, and we can make this windows bigger. And as you can see, this one is the UTM coordinates, the Y and the X, and these dots are the groundwater elevation according to the Wolfkamp aquifer data set. What we can see in this map is that the groundwater elevation is showing a trend, because the yellow dots are where the water is deeper, and the blue dots is where the water is more close to the surface, right? Because the groundwater elevation is based on the sea level. If you are interested to create this kind of maps in QGIS, I created a video tutorial at the GeoRGV community YouTube channel. Is this video over here, and I did the same kind of map, but in this case I was using the Muse River dataset related with contaminated soils. Then we can close this one, we can close this one, and the next step is to create the multiple regression model that is going to be based on second order trend surface. And remember that at the previous lesson we decided that the best model was the one related with the second order trend surface. Then if you want to know what is the reason because the second order trend surface is the best model, I'm going to invite you to review the previous lesson. Then in this lesson, for the generalized least squares, we are going to work exclusively with the second order trend surface. We are working now with the ordinary least squares for the second order trend surface, because before to do anything with the generalized least squares, we have to do the analysis of the structure of the second order trend surface for the ordinary least squares, okay? Then next step is to create the table where we are going to add all the values associated with this model. This model, remember, is the second order trend surface according to the ordinary least squares. Then we are going to create a table that we are going to call this table as residuals second table, and it's going to be the same as the A2 data frame, okay? Then we can run this one. And now we are going to add the residual values from this model to the table, okay? And then we are saying that this object is going to be equal to the residuals from the model 3. Remember that the model 3 is this one. Then we can run this one, and doesn't exist the model, because first we have to run this section over here, then run this one. Now we can run this one, and we can run this one, and now add the residual values to the table. To do that one, we are going to say that in this table we want to add a field that is going to be called like this one, and this field is going to be this value, and this value is the residual values from the model 3. Then we can run this piece of code, and we are going to do the same for the predicted values of the model 3. And now what we are going to add is a quality control where the residual plus the predicted values has to be equal to the groundwater elevation. We was explaining all this stuff at the previous video tutorial. That one is a reminder, right? Before, at the initial table, that it was the data set A, what we have is the ID, the X, the Y coordinates, and also the groundwater elevation. Then for each of these dogs, we have the X and Y coordinates and also the groundwater elevation. But now with the new table, is this one, what we have is the ID, the X and Y coordinates, the groundwater elevation, and also the residuals and the predicted values associated with the second order trend surface from the ordinary least squares. And also we added the quality control that it means that the summation of the residuals plus the predicted values has to be equal to the groundwater elevation. Then this value over here has to be the same as this value over here. If any of these values is not the same as the value over here, it means that we make a mistake. But in this case, as you can see, all the values are the same. That's the same as this one over here, right? The predicted value plus the residual value is equal to the variable of interest. In this case, it was the groundwater elevation. Previously, I make a mistake because I said that the highest values are closer to the surface, right? But that is not true because it depends on the topography. The only thing we can say over here is that the groundwater elevation is moving from the highest values to the lowest values, and these lower values are closer to the sea level because the elevation of the groundwater is based on the sea level. Then here we have a bigger distance because it's approximately 1000, and here we have a lower distance because it's around 200 meters above the sea level. Then at the end, what we can say is that the groundwater is moving from this area to this area over here, and that's the trend surface that we can recognize on the groundwater elevation. Now the next step is to analyze the structure associated with the second order trend surface for the residuals based on the ordinary least squares. Then we are going to use a couple of packages that is going to be the GStats and also the SP. Then I'm going to run these two libraries, and now I'm going to convert this table in a spatial points data frame, because in order to do the semi-variogram we need to add the coordinates, and that's what we are doing here. Because when we are working with the semi-variogram, we need the distance in meters, right? And in order to have the distance in meters, we have to tell the software that X and Y are coordinates. Then we are going to run that one, and we are going to see how this table is going to change from data frame to a spatial points data frame. Then let's go to run this one. As you can see, now we have a spatial points data frame. And now the first thing that we are going to do is the omnidirectional semi-variogram cloud of the residuals based on the ordinary least squares for the second order trend surface. Then this object we are going to call with this name, and here we have the script to produce the semi-variogram. Here we are using the residuals from the ordinary least squares, and we are saying that the variance is constant, and also we are going to use the data from this table, that is this table over here. And then we are adding the cutoff, that is 450,000, and that is the total distance from here to the over here, maybe the longest distance, okay? And also we are saying that we want the cloud of points. Then now we can run this script, and we can plot with the next one. Then we can maximize these windows to see the semi-variogram cloud based on the ordinary least squares for the residuals for the second order trend surface. As you can see in this cloud of points, we don't have any trend. The distribution of the pair of samples, it's pretty random, and that's what we want to see. Now, instead of creating the cloud of points, we are going to create the omnidirectional experimental semi-variogram. And the only thing is changing is just that here in this script, we remove the cloud to be true, okay, as you can see, but the rest of the information is the same. Then we can run this script. And also with the next one, we are going to plot the experimental semi-variogram, the omnidirectional one. Then we can make these windows bigger to talk a little bit about this graph. Important things related with this graph. We have the cutoff that is around 450,000, as we said previously at the script. Also here we have the semi-variance, and each lag distance is about 20,000 meters, and the number of pair of samples for each lag at the beginning at the correlated area of the graph is really good, and we can say these lag distance are representative, right? Because they have more than 100 pair of samples for each lag. Here at the end, that one is not that good, but it doesn't matter because all this area is not spatially autocorrelated. The spatial correlation of the data happens in this area of the graph. Another very important thing is to recognize that the residuals from the second order trend surface from the ordinary least squares are showing a structure, because we can recognize a nugget effect and also a partial seal. It indicates that our data has a structure, and it is not just pure nugget. If we have pure nugget, we are going to say that we don't have a spatial autocorrelation, but it's not this case. Then we can say also that we reach the seal approximately over here, where the lag distance start to stabilize, okay? Then the semi-variance is increasing over here, then reach the maximum over here, and then stabilize. Then we are going to say that the range approximately is over here, 120,000, maybe something like that over here. And the seal is going to be a little bit less than 3,500. And also we are going to have a significant nugget effect that is going to be a little bit more than 1,000. In this lesson, I'm not going to do a very deep analysis of the omnidirectional experimental semi-variogram, but if you want to have a better understanding, my recommendation is to follow the third geostatistics course at the GLS-RK community website at gscourse.online. The third course has more than 9 hours of content related to structural analysis. Now the next step is to be focused just on the autocorrelated area of the graph. Then it's going to be this area over here. To do that one, we are going to run the next script, and here what we are going to do is adjust the omnidirectional experimental semi-variogram of the residuals based on ordinary least square. Then if we don't specify any cutoff, the software is going to take 1/4 of the total distance. If the total distance, as we said before, it was 450,000, then 1/4 is going to be around 150,000 meters. Okay, that's the distance is going to take by default the GStats library. Okay, then as you can see here at the script, I didn't specify any cutoff. Okay, then it's going to take that distance by default. Also, the width, the lags, is going to be around 10,000. Okay, let's go to see now. Then we can run this one, and now we can plot. And we can make this screen bigger. Then here we have a sum of the correlated area of the graph, right? Because now the cutoff is a little bit more than 150,000, and we can see very clear the structure of the data. We can see that the semi-variance is increasing until over here, and then it is stabilized. Then we can say that the range is going to be around 100,000. The seal is going to be around 3,500, and the negative effect is going to be around 1,000. Also, now we have lags every 10,000 meters, and as you can see now, the number of pair of samples for each lag is a little bit less than before. The reason is that at the other graph, as the lag distance was bigger for each lag, we have more pair of samples. Then what we want is to have lags that are representative for the distance, right? Because we are going to fit the model according to these lags. Then any lag with more than 100 pair of samples is good and is going to be representative, right? Even 81 is not that bad. 87, it's, could be better, but it's not bad. And any value, lower than 20, something like that, we can consider that it is not really good, right? 35 is not the best, but it's like the limit, right? Then at the end, we have to look for an equilibrium between the number of lags, right, that we plot on the graph, and also the number of pair of samples each lag has, right? Because at the end we want to have several points to fit the model. We don't want to fit the model just with a few lag distance, right? Because that's true. If we decided to put a lag distance of 20,000, we are going to have less lags, but that lags are going to have more pair of samples, right? But we don't want to fit a model with just, for example, 5 lags. It's better to have more lags in order to have a better approximation when we fit the model. But also what we don't want to have is a lags with a very poor number of pair of samples. Now I can show you how you can modify all these values, the lags and the cutoff, okay? Because in this script, in this one over here, I decided to leave like that and leave the software to put the values by default. But you can specify, right? If I put here, for example, cutoff equal to, for example, 200,000. And also I can put the lag distance, for example, is width equal to 20,000. We can run now this script. You are going to see how it changes. Run and run. And now we have this one. And as you can see, now we have each lag. It is now 20,000 meters. And the total extension of the graph is about 200,000. As you can see now, each lag has more pair of samples, right? But the correlated area of the graph is this area over here. And in order to fit the model in this area, we have just 4 points, right? And before we have more information. And I believe that is better, right, to fit the model. Here we have more or less the same information, but I believe if you have more lag distance, the model is going to be fit better. Then what I'm going to do is remove that one because I want the values by default. But if you want to do a different approximation, you can decide what is going to be the lag distance and also what is going to be the cutoff, right? As you can see, here we have more lag distance, but in this case it's every 10,000 meters. Okay, now we can close and move on to the next thing that is going to be model the semi-variogram, okay? Then we can use this script to see what is the best model, okay? That one is going to be according to the to the software, okay? We are not taking any decision. We are putting this script over here, and we are saying from all these 4 different authorized models, what is the best, okay? What fit the best. Then we can run this one, and now we can see the results. Then here we have the nugget, that is 875, it's over here. Then we have the partial seal, that is this value. The model, the best model according to the software is the exponential one, is the one fits better on the data. And the range is this value, but as you can see, this value is over here, right? And that's not the real range. For the exponential model, we have to multiply this range by 3, and that one is going to provide the effective range, and the effective range is going to be around 120,000, and it's going to be over here. That's where the semi-variants reach the seal. Remember that at the exponential model, we are never to reach the seal, because the semi-variance is asymptotic with the seal. We are never to reach 100% of the seal, okay? Okay, now we can move on to the next thing, but first let me tell you that the model is going to be fit on the data according to the weighted least squares, okay? And this model provides more importance to the shorter lag distance, okay? Then it's going to be fit the model, giving more importance to this area of the graph. That's what the weighting least squares is doing, okay? The model is not fit according to the ordinary least squares, it's fit according to the weighted least squares. Then the next thing that we are going to do is create the model. Then to do that one, we are going to use the same script as before, but we are going to provide approximation values, okay? Then we are going to see the partial seal is approximated 2,500. The model I want is the exponential. The range, as I said previously, is the exponential. I mean is the effective range. And the nugget it's 800. Okay, the effective range is 120,000, okay? And 120,000 divided by 3 is the range. Then we can run this portion of the code, and we can see the results, and the results are going to be the same as these ones. As you can see, both of them are the same. In this case, we added approximately the values, okay? That's not the exactly values, but the software provides the exactly values. And now we can plot the model to see how it looks like, and that's the model. As you can see, here we have the nugget, and the range is over here. As I said previously, we are never going to reach the seal 100% because the model is asymptotic with the seal. Now we can close this one and move on to the next model. The next model is going to be the spherical model. I want to do both of them because, as we are going to see later, the exponential model is not going to be the best for the generalized least squares. Then I want to do also the spherical for the ordinary least squares because later we are going to compare everything, right? Then for the spherical model, we are going to put this name for the object, and it's going to be the same. We are going to use this script, fit-variogram. Then we are adding here the semi-variogram. This semi-variogram is the one we specify here at the top, is this one. And then we are going to provide the model. For the model, we are going to use this script, and the values again are going to be approximately, okay? But we have to specify that we want the spherical model. The range is going to be this one, and the nugget effect is going to be this one, okay? These values are approximately, okay? We need to put some values over here to initiate the computation, okay? But the software is going to provide the exactly values. Then run this one. Now we can see the results. And as you can see, the nugget is a little bit higher than the exponential model. The partial seal is a little bit smaller compared with the exponential model. Here we have the spherical model, and here we have the range. When we are using the spherical model, we reach 100% of the seal, okay? And that's the real range. And now we can plot. Then we can run this one, and that's the spherical model. At this point, I want to clarify something that could be a little bit confusing, okay? We get these residual values using the second order trend surface for the ordinary least squares, okay? But now we are fitting the model on these residuals according to the weighted least squares. They are two different things, okay? We are talking about different things. One thing is how we get the residuals, and another thing is how we fit the model on the data. Also, in this case, we leave the software to fit the model automatically, okay, according to the weighted least squares. But there are some scripts that you can fit the model manually, okay? You can add some values over here to fit the model manually. If you want to know how to do that one, I invite you to watch the 5th lesson of the 3rd geostatistics course that it was about modeling the semi-variogram, okay? Sometimes it's pretty useful to fit the model on the data manually, because maybe you have some very poor values over here and you are thinking that you don't want to use this lag distance over here to fit the model, and you want something more like this, you know, taking in consideration these values. And you can do all these things just plotting the model manually, okay? But in this case, as I said, we are going to do the process automatic. We are going to leave the software to fit the model automatically. Now, the next step is to work with the generalized least squares. Then what we are going to do is compute the residuals of the generalized least squares using the exponential model. First, we have to install this package. Now I'm going to add here a pound to avoid to run this package again. And now we can load the library. And now what we need is the proportional nugget from the exponential model. And we are going to use this script. We are going to call this object like this one. And this one is the relation between, let me show you over here. We are taking the exponential, is this model over here. Then we are looking for the relation between the seal and the nugget effect. Then we can take all these two. The summation of the nugget effect plus the partial seal is going to be the seal, and that value is going to be the 100%. And now we want to know how much represent just the nugget. To do that one, we are using this script over here. Then we can run this line. Let me go down with this one. Sorry. We can run this line. And the value for the relation is 25%, 25.5%. Now we are going to calculate the residuals for the generalized least square, adding first the second order trend surface, is this value over here, from the data that is located over here, using this model or method. And also what we are going to add is the spatial correlation. As you can see in this model, we add the trend surface associated with the second order, and also we are going to add the spatial autocorrelation that we get from the ordinary least squares. That it was this spatial autocorrelation, because first we are going to work with the exponential model, and then we are using this script to specify the correlation. Here we added the exponential model, and here we add the structure of the exponential model for the ordinary least squares. And also we want to specify that the nugget is true, and also we have the coordinates and x and y. Then we can run this script, and we can use two different methods, right? The restricted maximum likelihood, that is REML, or the maximum likelihood. Okay, I don't want to make a big explanation about this topic because it could be a little bit complex, but as a general estimate, we can say that we are using the restricted maximum likelihood when the number of samples are small compared with the predictors that we have, right? Here in this case we have 85 samples. That is not really big. Then we want to use this one. When we have a lot of samples, we can use the other one, the maximum likelihood. Also, I would like to tell you a little bit more about how we can add the structure to the model, okay? And this one, if we run this line, you are going to see that here what we are saying is just the range, okay? Let me show you. The range for the exponential model is this one, and this value is the same as we have over here, okay? And also for the next one, what we are adding is the proportion of the nugget in the model, okay? This one is the same as this one. We can run to see the value, as we said previously, is 25.5%. And in this way is how we add the structure of the data, okay? We are trying to calculate the residuals for the generalized least squares using the structure of the ordinary least squares, okay? That's the point. But also in this model, we are adding the second order trend surface, okay? That's how the model of the generalized least squares work with this package. Now we can see the class of this new object, that is the model. Sorry, this one is this model over here, and that's the object that we created over here. Then we can see the class, and the class is generalized least square, and now we can see a summary of the model. What we have here. Here we have the generalized least squares fit by the restrictive maximum likelihood. What is our model? The second order trend surface. Also we have the RK number informations, but as we are using this method, don't pay attention to these numbers because it doesn't work with this method. It works with just the maximum likelihood, okay? Then we have here the correlation structure for the exponential model. Here we have the formula indicating that we are using the x and y coordinates. Here we have the range that this model gives us according to the second order trend surface plus the structure of the exponential model for the ordinary least squares. And as you can see, this value, it doesn't make any sense. Also, the summary provides the proportion of the nugget effect compared with the seal. And again, this value, it doesn't make any sense. Then as a conclusion, we can say that we cannot use the structure of the exponential model for the ordinary least squares to predict the residual values using the generalized least square model, okay? Because it doesn't provide values that are realistic. Then the next step is to do the same, but in this case using the spherical model, okay? As I indicated over here, exponential model doesn't work as it provides unrealistic range and portion of the nugget. Then we are going to run the next lines. Run, compute the residuals of the generalized least squares using the spherical model. Then first we are going to calculate the proportion of the nugget compared with the seal as we did previously, but now we are changing the name, nugget proportion for the spherical model. Okay, before we did the, how we call before, it was nugget proportion for the exponential. Then we can run this one, and we can run the other one to see the value. Now for the spherical model, the nugget represents 31.4%. Okay, and now we can again calculate the residual values, but in this case using the structure of the spherical model. We have the same as before. We have the second order trend surface, but now we want to use the structure associated with the spherical model for the ordinary least squares. Then we can run this one. Now see the class. Again, this is a generalized least squares. We can see a summary of the model. And here we have the same. We have generalized least squares fit by the restrictive maximum likelihood. Here we have the model for the second order trend surface. Here we have the Akai numbers that we are not going to use because we are using this method. And here we have the correlation structure that is associated with the spherical model for the ordinary least squares. Here we are using the X and Y as our coordinates. And here, as you can see, now we have a value of the range that makes sense, right? We want to compare this range with the range that we got when we was using the model of the ordinary least squares, okay? If there has to be pretty similar, right? And also the nugget effect, it makes sense, right? It represents 23.4% compared with the seal. You have to understand that this model, this one over here, is pretty complex, right? And sometimes the model doesn't work really well. Then we need to compare the results with the results that we get on the model of the ordinary least squares. Because if they are too much difference, it means that this model doesn't work well, okay? Then that's the reason because we need to compare. And in this case, when we compare the range and also the nugget with the results that we got when we was using the ordinary least squares, you can see that they are pretty similar, right? I'm going to show you now. That's for the spherical model, right? We have here almost 100,000, and the range is this one over here, right? That it represents, I mean the range, the nugget represents, we say, we calculated over here 31%, right? And here for the generalized least squares, what we have is a range that is 124,000, and the portion of the nugget is 23%, right? They are pretty similar values. That in this case, we can say that the generalized least squares from the spherical model, from the structure of the spherical model for the ordinary least squares, it makes sense, right? The data makes sense. Then the next step, we are over here, we run already this one, right? That is the summary. As you can see over here, now we can run the next line. And with this line, I put the spherical model for the ordinary least squares to compare with the results that we get for the generalized least squares. But we compare already, right? Then the next line is going to be the structure of the new object, the model related with the generalized least squares. Here we can see all the information inside this model. You can take a look. And also with the next line, what we are going to do is extract the residuals. We are saying that this object, residuals generalized least squares, is equal to the residuals from the new object we created related with the generalized least squares, okay, for the spherical model for the second order train surface. Then when we run this one, we add here a new object that is values related with the residuals for the generalized least squares. We are going to do the same for the predicted values associated with the generalized least squares. Now we can see a summary of the residuals. Here we have the minimum, the maximum, the first quantile, the median, the mean, and the third quantile. And also I put here the same but for the ordinary least squares, okay? That was the summary for the ordinary least squares. Then we can compare the residual values here, right? These residual values are for the generalized least squares, and these residual values are for the ordinary least squares. Next thing that we can do is just view the table associated with the residuals of the generalized least squares. And here, as you can see, we have the values. Then the next thing is to add to the table, to this table, let me check over here, is this table over here. And if we take this table over here now, what we have, we cannot check the table because it's a spatial point data frame, but okay, we cannot check that table now. But in this table, what we have is the ID, the X and Y coordinates, because we saw previously is this one over here, right? We have all these values. We have the ID, the X, the Y, the groundwater elevation, the residuals associated with the ordinary least squares, the predicted associated with the ordinary least squares, and the quality control associated with the ordinary least squares. Now what we want to add is the residuals of the generalized least squares, right? And we are going to add this new field to the table that is going to be equal to these values over here. Remember that these values over here and these ones are the residuals from the model of the generalized least squares with the structure associated with the spherical model with the second order train surface. Also, it is interesting to indicate that when we get these residual values from the generalized least square, we are using the second order train surface and also the structure of the spherical model, right? But when we was working with the ordinary least square, we get the residuals just using the second order train surface, okay? There is big difference over there. Then we can add now this field to the table, run. Also, we are going to do the same for the predicted values. Run. Oh, sorry, not this one. I want to run all together. Run. And now I'm going to add the same as before. I'm going to add a quality control. This quality control indicates that the residuals from the generalized least square plus the predictors from the generalized least squares has to be equal to the groundwater elevation. Then we can run this one. And now we can see the table, but I'm not sure if we can see this table. Okay. As we cannot see the table, we are going to run the next script that is going to convert this table in a data frame, just to see the table. And we are going to save this new table with this name, residual second order train surface table for the generalized least square. Then we can run this one. And now we can see the table with the new data. we have the same table as before, but we added the residuals from the generalized least squares and also the predictors for the generalized least squares. The summation of this one plus this one has to be equal to the groundwater elevation. Then we can compare this value over here with this value over here, and we can see that both are the same. We can compare some of them to verify that everything is correct, and it is good. With the next line, we can see the names of this table. And run. We have all these parameters in the table. And now we are going to create a backup of this table that we are going to call with the same name, but adding a number 2. Then create the backup of the table. And what we are going to do now is to create the omnidirectional experimental semi-variogram with the residuals of the generalized least square that we add to this table. Okay, let me show you here the table. Now we have this table that we have the generalized least squares for the residuals and also for the predictors. We want to take these residual values to do the structural analysis, okay? Previously, we did the structural analysis for the residuals of the ordinary least squares, but now we are going to do the structural analysis for the residuals for the generalized least squares, okay? Because we want to see that the values that we get, they are good, okay? They make sense, they are realistic, okay? Then to do that one, we did the backup because we have to convert this table, this new table, in coordinates. To do that one, we are going to use this script. Then now we are going to create the adjust omnidirectional experimental semi-variogram of the residual based on the generalized least squares. Then here we are saying that the residuals from the generalized least squares has a constant variance or constant semi-variance, and we are going to get the data to do that one from this table. Okay, that's the table that we change here to a spatial point data frame. Okay, it's this table over here, this one. And as before, we are not going to add any cutoff or any lag distance. We are going to leave the values by default. Then run this line. And now we are going to plot the new one. Let me run this script over here. And this one is the results. This one is the residuals from the generalized least square for the second order trend surface using the structure of the spherical model. Then we can close this one, and now we can fit the model associated with the exponential on that residual values from the generalized least squares. Then we can run that one, and we can plot this one. As you can see, the values that we get here, they are no good, right? Because we have to multiply the range by 3, right? Then when we compare these values with the values that we get when we was working with the ordinary least squares, we can see that the range in this case is 3 times bigger. Okay, and that is too much. Even these values doesn't match with the results that we get when we was working with the model of the generalized least squares for the exponential model. Now we are going to do the same, but with the spherical model. Again, we are using the residuals from the generalized least squares. Okay, then we can fit the model. See the results. The results are pretty consistent compared with the results that we get at the generalized model. And now we can plot the model. And here we have the results for the spherical model on the residuals from the generalized least squares. In this case, as you can see, the model makes a lot of sense and looks pretty good. Then we can do now a histogram to verify the normality of the data, okay? Then we are going to do a summary of the residuals from the generalized least squares, okay? Then, as you can see here, for the maximum, for the minimum and for the maximum, that the residuals from the generalized least squares are pretty symmetric. Here you have the first quantile, and here you have also the third quantile. The only thing it calls my attention is that the mean value is not zero. The mean value of the residuals is not zero, as we indicate over here. Then this is because the generalized least squares include the spatial correlation in the model as well as the normal distribution of the data, right? Then when we are working with the generalized least squares, the goal is to have the coefficients in an optimum way to include the spatial autocorrelation of the data, right? And we cannot have everything, right? We cannot have the ideal coefficients with a zero value for the mean, right? Then the software is trying to have the better equilibrium, right? Have a good coefficients and also have a mean that is close to zero, right? But it is not zero. Now we can plot the histogram. I did the histogram with the ggplot because it's more nice, right? But first let me run these two lines. And as we can see at the histogram, we have a pretty normal distribution, but the mean value it's not a zero, it's over here. And also the median, it's not at the same location, but as you can see, the distribution it's pretty normal, okay? It's good. Then the next thing is to create the grid to interpolate the predicted values from the generalized least squares model using the second order trend surface. Let me first remove this line that is not right. And now what we are going to do is to run all these piece of code together, because we are not adding anything new here. We explain everything related with how to create the grid at the first part of the third lesson. Then if you want to see how to do this stuff, just take a look of that lesson. Then I'm going to run everything together. Now is to take this grid and interpolate inside the predicted values according to the second order trend surface with the generalized least square model. Then we can go here and we can run the next things. Second order trend surface based on generalized least squares, interpolate the data inside the grid, predicts this function, computes the best fit, and what we need is to have the grid as a data frame. That's because we make this conversion over here. Now where we are creating this object that is going to be the prediction for the generalized least squares for the second order trend surface, we are using the script predict, and we are going to add the model that we created for the generalized least squares based on the spherical model for the second order trend surface, and we are using this grid. That's the one we created over here, and that's it. We can run all this together, and now we can see the class. The class is a numeric, and we can see a summary of the new object. We have this information that is inside this grid. We have the minimum value for the predicted values is this amount, and the maximum value is this amount. And then we have the first, the median, the mean, and the third quantile. Now also we can create a table to see all these values. Now I'm not really sure what is not showing the table, but it's not a big deal. We don't need it. Maybe we don't have enough resources in this virtual machine to see the table, because has a lot of values. As you can see over here, this object second is this one over here and has a lot of values to show in the table, but it doesn't matter. Let's go to carry on. Now we are going to convert the grid a spatial point data frame. To do that one, we are going to convert this object with coordinates. Then we can run this one. And now we are going to create the grid with the predicted values as a spatial point data frame. To do that one, we are going to use this script. Also, all these things were explained at the previous lesson, but because we was doing the same, but in that case it was for the ordinary least squares, and in this case is for the generalized least squares. Then we are going to convert the grid as spatial pixel data frame. The object are points in a regular grid. Then just run. Now we are going to run the next one, improving the computational efficiency by using the full grid. And also we are going to assign the reference coordinate systems to the new grid. And also we are saying that this one is going to be inside this one over here. This one is this projection. We have to do this one now. Now the next one is checking the statistics and characteristics of the new grid. Here we have the information about the extension of the grid, the minimum and maximum values, the projection that we are using, the number of pixels that we have, and also the dimension of the cells, and the values that we are adding inside the grid. That is the predicted from the generalized least squares from the second order trend surface. Then we can create the graph. Create a graph where we plot just the fitted values. And we can print. And this one is the result. Now, the next thing is to convert the new grid a data frame in order to manipulate the variables. Then we are going to do that one, and we are going to see, we are going to convert this one in a data frame to see the values inside the grid. Then let's go to run this one. Let me start here. View. And here we have the x coordinate, the y coordinates, and the predicted generalized least squares for the second order trend surface for each of the pixels of this grid. Then now we are going to fix the columns, because what we want is the x to be the first, the y to be the second, and the predicted values to be the last column. To do that one, we are going to use this script. View. Now it's fixed. The next step is to create a raster with the new data set. Is this one over here. To be exported to QGIS, then we need to use the library raster to create the raster. We are using this script to create the raster. And now we can plot the raster. As you can see, we cannot see well. We can clean everything. We can run this one again. And here we have the final result. Now we are going to export. That one is the second order trend surface according to the linear regression, that is the generalized least squares. And we can remove this one here. Then we want this one, that is this object. This object is the same as this one, and we are going to save with this name. And that's it. Then we can run this one. And with the next script, we can see the files that we have in that folder. Is this one, then we can check. Is this image over here. Now we can run the QGIS while we finish the coding. Now the next thing is to export the spreadsheet for the residual values to perform the ordinary kriging. Then we are going to export the table where we have the residual values and the predicted values associated with the generalized least squares. And that spreadsheet is going to be saved in this folder with this name. This name, and in this folder. Then we can run this script. Run. And now we can check that spreadsheet. That has to be saved in the data set. Is this one over here. Okay. And now we have a spreadsheet that can be opened in QGIS with the residual values and also the predicted values for the generalized least squares. We can use the residual values to make the interpolation of kriging, ordinary kriging, with QGIS using these values over here. Then we can close this one. We can open QGIS. We can open the last project. That it was this one, I believe, lesson 2. It was this one. Here we have for the ordinary least squares, we have the first order trend surface and also the second order trend surface that it was from the previous lesson. That now we are going to add the new one from the generalized least squares. That is just the second order trend surface. Then lesson 4, this one, generalized least square, this one, and it's going to be this one. Open and add and close. Now we want to add the reference coordinate systems. That is this one. Okay. Now we are going to make some modifications on properties. Then go to single pseudo color, single band pseudo color. Here is going to be equal intervals, and I want 10 intervals. 10 intervals, and also I want here discrete. Apply, and okay. Now we can move this one here at the middle. And this one is the first order trend surface from the ordinary least squares. This one is the second order trend surface from the generalized least squares. And this one is the second order trend surface from the ordinary least squares. We can compare the difference between this model and this model. And here you can see the differences. Then the one we want to use is this one that is related with the generalized least squares, because the coefficients to build the second order trend surface are optimum according to the spatial autocorrelation of the residuals based on the generalized least squares. Now, as we have the trend surface, in order to complete the regression kriging, we have to do the ordinary kriging with the residuals from the generalized least squares. Then after creating the raster with the ordinary kriging, we can plus these two rasters in order to have the final results. But in this case, we are not going to do the ordinary interpolation. Maybe in a different lesson, we can take a model to plus the trend surface plus the ordinary kriging, but I didn't decide yet what model is going to be, okay? Then at this point, I'm going to finish the video. Thank you very much for watching and see you on the next lesson. Remember to save the things you did on the RStudio. Just press save. Select the folder. This folder is good. Generalized Least Square. Save, and then you can close this one.